Hello everyone and welcome to the video. In this video, we're going to design a system for obtaining desired speed from a DC motor. For that, we'll be modeling the system, analyzing the system, and designing a controller and then simulating the entire system using MATLAB. Here, we'll be designing a PID controller, root locus controller, and frequency domain controller. For modeling the system, we'll consider the electric equivalent circuit of the armature and the free body diagram of the rotor. The input to the system is taken as the voltage source applied to the motor's armature and the output as the rotational speed of the shaft. The rotor and the shaft are assumed to be rigid. Assuming the magnetic field to be constant, the torque is related to the armature current I by the relation T is equal to Kt into I. The back EMF E is proportional to the angular velocity of the shaft by the relation E is equal to Ke theta dot. In SI units, the torque and back EMF constants are equal, therefore we'll substitute them with K. And using Newton's second law and Kirchhoff's voltage law on the figure above, we obtain the equations J theta double dot plus B theta dot is equal to Ki and L di by dt plus Ri equal to V minus K theta dot. In this equation, J is the moment of inertia of the rotor and B is the motor viscous friction constant. Applying Laplace transform to equation 3 and 4, we obtain equation 5 and 6 in terms of the Laplace variable s. By eliminating I of s between the above two equations, we arrive at the following open loop transfer function for our system, where the rotational speed is considered the output and the armature voltage is considered the input. To express the governing equations above in state space form, we can choose the rotational speed and electric current as the state variables while keeping the armature voltage as the input and the rotational speed as the output. We obtain the following equations. The physical parameters for our system are as indicated. Now let's talk about our design requirements. The most basic requirement of a motor is that it should rotate at the desired speed, and therefore we'll require that the steady state error of the motor speed be less than 1%. Another performance requirement for our motor is that it must accelerate to its steady state speed as soon as it turns on. In this case, we want it to have a settling time of less than 2 seconds. Also, since a speed faster than the reference may damage the equipment, we want to have a step response with overshoot of less than 5%. In summary, for a unit step command in motor speed, the control system's output should meet the following requirements: settling time less than 2 seconds, overshoot less than 5%, and steady state error less than 1%. With the conditions in place, let's now try to analyze our system in MATLAB. Using the MATLAB code, we've defined the various physical parameters of our system, its transfer function, as well as the various matrices comprising its state space. As shown in the 11th line of the code, with an increment of 0.1 seconds between 0 to 5 seconds, we've obtained the step response of the system. For the given step input, the final value should be 1. And since the steady state error should be less than 1%, we can understand that our final value being 0.0999 is much smaller, which means the steady state error is very big. Therefore, the speed is 10 times smaller than our desired speed, and the motor takes 2.07 seconds as opposed to our 2-second settling time criterion. Fortunately, there is no overshoot. Now that we have a large steady state error, we need to bring this steady state error down. For this, we use a proportional controller. On the left window, we have the code for a proportional controller with the proportional gain Kp equal to 100. Now let's obtain the step response for Kp equal to 100. We can see that though the steady state error has decreased, the percentage overshoot has increased manifold. This is not what we want. If we increase the value of Kp to 500, then we can see that again the overshoot has increased multiple times. We have also plotted the step response for Kp equal to 10. As expected, the steady state error has decreased, but we still have the problem of the overshoot. Due to this problem of the increased overshoot, we can understand that a simple proportional controller will not be able to meet our design requirements. We'll need to have, therefore, a PID controller. So let's have the code for a proportional integral derivative controller for various values of Ki, that is the integral gain, and the Kd, that is the derivative gain. From trial and error, we've come to understand that the controller that we require needs large Ki and large Kd, because for small Ki and small Kd, the settling time is very high and therefore undesirable. Whereas on the other hand, a large Ki and small Kd will result in an undesirably high overshoot. As it turns out, with a large Ki and large Kd, our overshoot requirements as well as the steady state error requirements have been met. We can also observe that our settling time requirement has also been met. Thus, with Ka equal to 100, Ki equal to 200 and Kd equal to 10, we've been able to meet our three desired conditions. Now that our three criteria have been satisfied, we need to add a controller to the system. The main idea of this frequency-based design is to use the Bode plot of the open loop transfer function to estimate the closed loop response. Adding a controller to the system changes the open loop Bode plot, thereby changing the closed loop response. It is our goal to design the controller to shape the open loop Bode plot in such a way that the closed loop system behaves in a desired manner. From the first Bode plot, it appears that the gain margin and phase margin of the system are currently infinite, which means the system is robust and has minimal overshoot. The problem with this is that the phase margin is infinite because the magnitude plot is below 0 decibel at all frequencies. This means that the system will have trouble tracking various reference signals without excessive error. Therefore, we'd like to increase the gain of the system while still achieving enough phase margin. A phase margin of 60 degrees is generally sufficient for stability margin. From the second Bode plot, this phase margin is achieved for a crossover frequency of approximately 10 radian per second. The gain needed to raise the magnitude plot so that the gain crossover frequency occurs at 10 radian per second is approximately 40 decibels. Therefore, the exact phase margin for a gain crossover frequency of 10 radian per second is 56 degrees. The gain needed to raise the magnitude plot so that the gain crossover frequency occurs at 10 radian per second is 37.2 decibels. By using the command indicated, we can get the exact values of phase and magnitude at 10 radian per second. From these values, we can understand that 37.1 dB of gain must be added to the system. Otherwise stated, a proportional gain of 72 will achieve an open loop gain of 1 at 10 radian per second. This proportional gain of 72 is used to plot our next step response. Now, the settling time is fast enough, but the overshoot and the steady state error are too high. We can reduce the overshoot by decreasing the gain in order to achieve a larger phase margin, but this would cause the steady state error to become even larger. In this case, a lag compensator can be helpful in that it can decrease the gain crossover frequency in order to increase the phase margin without decreasing the system's DC gain. We'll be using the following lag compensator. This lag compensator has a DC gain of 100, which means it will increase the system's static position error constant by a factor of 100, and it will reduce the steady state error associated with the system's closed loop step response. In fact, it allows us to reduce the proportional gain of 72 used earlier while still meeting the requirement on steady state error. We'll employ a gain of 45 in this case. Furthermore, since the corner frequencies of the pole and 0 are a decade or more below the current gain crossover frequency of 10 radian per second, the phase lag contributed by the compensator shouldn't adversely affect performance much. With the lag compensator in place, the step response meets our three primary conditions. After employing frequency domain methods for controller design, let's now employ root locus methods. The main idea of this method is to predict the closed loop response from the root locus plot, which depicts possible closed loop pole locations. We can add zeros or poles via the controller to this root locus in order to achieve a desired closed loop response. Using the control system designer tool of MATLAB, we'll set design requirements such as setting time and percentage overshoot. So here we have the code to obtain the root locus, and as you can see, the control system designer tool has been enabled. This is the root locus of our transfer function. So let's proceed to enter our required criteria, settling time 2 seconds and percentage overshoot 5%. The two rays centered at the origin represent the overshoot requirement. The smaller the angle these rays make with the negative real axis, the less overshoot is allowed. The value highlighted is the corresponding loop gain. The vertical line at s equal to -4 represents the settling time requirement, where the farther to the left the closed loop poles are located, the smaller the settling time is. Clicking on the pink boxes and dragging them along the root locus to the desired location automatically modifies the controller to place the closed loop poles at the indicated position. We can now see the closed loop step response with the new gain. From this, we can see that there is no overshoot and the settling time is less than 1 second. Therefore, two criteria have been satisfied. However, we can also observe that the steady state error is approximately 50%. If we increase the loop gain to reduce the steady state error, the overshoot will become too large. In this result, the overshoot and settling time criteria were met with the proportional controller, but the steady state error requirement was not. Hence, we introduce a lag compensator and add poles and zeros. As shown previously, we change the closed loop pole locations and check if the step response meets the requirements and then find the desired loop gain. Moving the closed loop pole out of the overshoot requirement line will increase the percentage overshoot, but here we are moving out of it by ensuring it is below 5% for the desired lag compensator. And finally, we can observe that the settling time is less than 2 seconds and the steady state error and the overshoot requirements are still met. The equations we already know are assigned to the system model as shown below. The various components have been assembled. The input is the voltage source and the output is the speed. The components include a resistance, inductance, inertia, integrator, damping, etc. The various components in the system model can then be reduced to a single subsystem block as shown. As previously decided, we now introduce the lag compensator and then provide a step input to finally obtain the output. In this fashion, we have designed the system for obtaining desired speed from a DC motor. Thank you.